Alright, in this video we're going to start out by taking a look at a logistic growth model. And again, this is another one in a situation that shows up a lot in terms of population. And we talked about this one earlier. Sometimes it comes in the form of something that's increasing quickly, eventually hits a certain point, and all of a sudden the rate of increase slows dramatically until it reaches almost a horizontal asymptote when we hit our model. So again, we take a general form for our equation that's going to look something like this. We're going to start out with a value of y, which is going to find our population size, and some constant a, which we'll deal with in a second here. And then on the bottom, 1 plus another constant b times e raised to the negative rx, where x is time, r is usually going to be a rate. So on this one, the problem we're going to look at, on a college campus of 5,000 students, one student returns from vacation with a contagious and long-lasting flu virus. The spread of the virus is modeled by this formula. So again, if you notice, it does match up with our logistic growth model that we had up here, other than we've got our values plugged in now. So again, the y value is going to be the total number of students that are infected after t days. So on this one, the college also decides that they'll cancel classes when 40% or more of their students are infected. So we're going to be asked to find two things here. One, how many students infected after 5 days, because this is going to kind of show how quickly this thing can spread based on this model. And then, how many days will it take before the college will have to cancel classes? So let's start out with the first part here, after 5 days. So that's going to be our value for t that we're going to substitute in. So we're just going to rewrite our equation here with t substituted in with 5. So we get 1 plus 4999 times e, and then that's going to be negative 8 times 5, which is just negative 4 once we multiply that. Alright, so now this one's actually all set up for us, and this one is fairly simple. Really not much to do on this one other than hit the calculator and simplify. So we could get our value on the bottom, divide 5,000 by that value, and this one actually turns out to be approximately 54 students. So once we've got everything substituted in, it just becomes calculator work on this problem. So one student comes back to campus with this flu virus, it only takes 5 days, and all of a sudden we've got 52 or 54 people infected. So there's our fast spread, probably on this part of our graph right here. Now the second question we're looking for, we want to know after how many days will a college cancel classes. So our setup on this one is we have to figure out 40% of 5,000 students, and that's 2,000 students. So that's our 40%. So we're going to set up our equation here where 2,000 would be the number of students, our magic number. When we hit that number, we know that we're at 40%, equals 5,000 on top. And then on the bottom, a little different this time, not quite as quick and simple as the last one. This time our t value is what we're actually trying to find. So negative 0.8 times t. Alright, so a couple things that we can do on this one. One, we're going to get rid of this fraction by multiplying this all over to this side. So we're actually going to get 2,000 times our denominator. This is just letting us cancel our fraction. And that equals 5,000. Now I can divide both sides by 2,000. So this is going to disappear on the left side, and I'm going to be left with 1 plus 4,999e raised to the negative 0.8 times t. And again, 5,000 divided by 2,000 is 2.5. So I can subtract 1 on both sides to cancel this out. So I'm going to be left with 4,999e, all raised to the negative 0.8t. And then the 2.5 minus the 1 is 1.5. Slide it up here so we get a little more room. I'm going to divide both sides by 49.99 to isolate the e. So I get 1.5 over 49.99. And again, I could multiply or divide this out, but I want to keep it as exact as possible, as long as possible. So we're going to simplify over here. That e still has its exponent, negative 0.8t. So I'm going to do a natural log on both sides. I'll put this in parentheses since I'm eventually going to hit that up with the calculator. So again here, base e and an e, my exponent is my simplified left side, negative 0.8 times t equals all of this. And then negative 0.8, or negative 0.8, is the same as negative 4/5. So I'm just going to do reciprocal of that to get t by itself. And that's going to give me negative 5/4 on the right side. Trust me, that's a 5. Times my natural log of all of this. So this one eventually simplifies out once we hit the calculator up for a little help here. And simplify this, comes out to be approximately 10.14, or approximately 10 days. So very quickly this virus spreads so that 40% of the population of 5,000 students on this campus will be infected based on our logistic model here, all within a matter of 10 days. So kind of lets you see how quickly some of these things can spread. Alright, let's take a look at one last model in this chapter. And this is one that we see quite a bit. And this one dealing with intensity and magnitude of earthquakes. And the magnitude, that's what we're used to seeing on the news reports and everything. That's our Richter scale. So on this one, our R value that we see up top is our magnitude, or the value you get on the Richter scale. The I would be the actual intensity of that earthquake based on 1 being a minimum intensity. So here's our logarithmic model that we're going to set up, a log of I over I sub 0, and that's going to help us find our magnitude. So we're going to compare 2 different earthquakes from 2008 and see what we can figure out about their intensities and how they compare to each other. So in 2008, Nevada had a 6.0 magnitude earthquake on the Richter scale, while also in that year, eastern Sichuan, China, had a 7.9 magnitude earthquake on the Richter scale. Now, when we're used to just looking at a decimal system and a base 10, it looks like 6.0 to 7.9 is not that big of a difference, 1.9. But since this is a scale score, it doesn't really tell the whole story. So what we're going to do is we're going to find the intensity of both earthquakes. So we're going to start out with our Nevada earthquake. So we're going to start this out. And remember, I sub 0 is just 1. So really, I don't have to put anything there because it's just going to become r equals log of I. So on this one, magnitude 6.0 was what we start out with our Nevada quake. So that's our R value. So 6.0 is equal to log of I. And now, since this is just a common logarithm, it's going to be a base 10, we can just use our shortcut and do the circle. 10 raised to the 6th power equals I. Well, 10 to the 6th is 1 million. So on a scale where 1 is a minimum intensity, this one had an intensity of 1 million. Now again, a number by itself like that doesn't tell a whole lot, so like I said, we want to make a comparison here. So let's go with the 7.9 in China. So we would do 7.9 equals log of I, and we'll just do our same thing here. This is base 10 raised to the 7.9, and that equals I. And I'm not going to do 10 to the 7.9 in my head, but if we simplify this one, it comes out to be approximately 79,400,000. So now back to that scale score based on the Richter scale. We said that 7.9 and that 6 to a lot of people doesn't seem like a big difference because it's only 1.9 in the decimal system. But now if we were to compare these two more specifically, we would set this up and check our ratio. So the China earthquake, at 79,400,000 intensity, compared to the Nevada earthquake, which had an intensity value of 1 million, once we reduce everything here, and then drop our zeros here, drop our zeros here, and divide everything by 10, we're going to get approximately 79.4 times more intense. So now that makes it a little more easy to understand that just this 1.9 decimal change on this scale score actually meant that it was 79, almost 80 times more intense than the earthquake was in Nevada. So a lot of powerful information we can get using our exponential and our logarithmic functions.